Migration. Thank you. A promising alternative is to the migration logic above the OS layer into the language virtual machine. Language virtual machines such as Java and WebAssembly abstract away ISA differences. Several previous studies achieved live migration for Java, OCaml, and WebAssembly interpreters, but those methods rely on interpreter-based virtual machines, so they are limited. So they are very slow execution. So let's compare hypervisor-based and interpreter-based approaches. A hypervisor-based system such as CRU and then captures a low native process state such as CPU register and memories. Because of its simplicity, its advantage is performance, and it incurs no runtime overhead until live migration happens. But program and their snapshot are ISA specific, so you can only restore on the same architecture as the host node. And interpreter-based interpreter-based system instead serialize the VM state into internal state, such as bytecode program counter and stack frames and heap object. And that state is portable across ISAs. But the problem is performance, because interpreted execution is very slow. So in this work, we improve interpreter-based solution by using ahead of time compilation, shortly AOT. And our method bridges a gap between high performance and cross ISA portability. So our goal is to design a cross ISA live migration technique that achieves both portability, which means a program is migratable between different architectures, and also our method achieves high performance. And our approach is to develop a WebAssembly AOT compiler that adds machine code level instrumentation to support efficient checkpoint and restoration of programs. And in the figure below, the compiler compiles WebAssembly into the native executable. And this executable can migrate between, for example, x64 and ARM64. So let me briefly explain about WebAssembly. WebAssembly, shortly WASM, is a portable binary format designed for safe and efficient execution. And WebAssembly uses stack-based virtual instruction set similar to Java bytecode. And each variable in WebAssembly module is statically typed, so it is suitable for AOT compilation. And WASM can be generated from languages, general programming languages such as C, C++, Rust, and Go. Although originally WebAssembly is designed for browsers, it's now widely used outside the web. And next, a WASM module contains functions, global linear memories, and tables, which are used for indirect function calls. And these abstractions make WASM execution portable. On right-hand side, we can see an example of WebAssembly function. This function returns a double of a parameter of type i32. And the first bytecode, local.get, pushes a parameter on a value stack, and the second bytecode pushes constant i32 on a value stack, and then the third bytecode, i32 multiply, pops those two values from a value stack and pushes a product of them. So WebAssembly natively does not support live migration functionality, so we need to implement some functionality to achieve live migration for WebAssembly programs. And to migrate a WebAssembly program, its runtime state has to be portable. And similar to previous researches, our approach reuses the program state of a WebAssembly interpreter as the snapshot format. And the snapshot represents abstract WebAssembly state, which contains the program counter and call stack, locals, and linear memories. during migration, the source runtime checkpoints this WebAssembly state and transfers this snapshot into the destination runtime. And then the destination node then reconstruct the state and resume the execution. For example, a WebAssembly program precompiled x64 can migrate to another host where the same program has been compiled to ARM64. Only the snapshot data moves between them here. So to enable live migration for AOT compilers, we need to instrument code to checkpoint and restore the execution. So here we considered two options. First one is WASM level instrumentation, and it transforms WebAssembly bytecode and insert the bytecode to checkpoint and restore. So this approach needs no runtime support, but the resulting binary is large and very slow. And the second approach is machine code level instrumentation. It inserts machine code or compiler intermediate representation during lowering WebAssembly into machine code. And this approach is small binaries compared to the first solution, and it incurs only low runtime overhead. But it requires runtime support to capture and reconstruct program state. For these reasons, we choose the second option because we focus on performance. And AOT compiler normally strip away all WebAssembly type information during lowering WebAssembly into machine code and compiler optimization. And this makes it hard for the runtime to reconstruct a WebAssembly level snapshot from row-level CPU registers and memory. So our key challenge is therefore how to rebuild WebAssembly state from optimized machine code without losing type information. So we leverage a technique called on-stack replacement, shortly OSR. And in JIT compiler, OSR switches between bytecode and optimized code. And OSR is also used for tiered JIT compilers. And in such cases, OSR switches between different level of optimized code. And OSR is implemented with a data structure called stack maps. And this data structure records where each program variable is located in register or memory. So we extend this concept of OSR to live migration of AOT compilers. So during a checkpoint, OSR translates a native code stack into a virtual WebAssembly stack. During restore, it reconstructs a native frame again. This allows us to capture and reinstantiate the execution state safely at certain program point. So for example, to make a checkpoint, the runtime performs OSR exit to convert its native program state into virtual WebAssembly state. And then the runtime can save this virtual WebAssembly state as a snapshot. On the other hand, to restore the execution, the runtime performs OSR entry. This is the opposite operation of OSR exit to convert the virtual WebAssembly state into native program state. So that it can reconstruct the state from virtual WebAssembly state to some CPU registers or native memory. So here in this slide we introduce a new concept, migration point. And migration point represent program point where the program can be checkpointed and restored. At each migration point, a tiny code snippet shown below in this slide is inserted. This code snippet checks whether a migration request has been issued, and if the migration request is triggered, then the runtime starts checkpoint operation. For example, it unwinds the code stack. So, however, pressing a migration point after every bytecode instruction would cause heavy overhead. Instead, we insert migration point only at function entries and loop bodies. Here we insert migration point at the loop inside the loop bodies so that we make sure that the runtime can migrate even when it executes in the infinite loop. So these program points correspond garbage collection save point, where the garbage collector typically starts garbage collection. And this design reduces runtime overhead while making sure that the program can be migrated. However, migration point act as a compiler optimization barrier. So certain compiler optimization, such as code motion and dead code elimination across the migration point are disabled. Otherwise, the runtime could no longer reconstruct the correct WebAssembly semantics, and it diverges from the original semantics of a WebAssembly program. So, and in implementation, we implemented these ideas in a prototype compiler called Wanko. And Wanko is based on the Wazuka compiler, which compiles WebAssembly to object files with LLVM compiler infrastructure. And we extend Wazuka compiler to insert instrumentation mainly during the lowering from WebAssembly into LLVM IR. And Wanko also has a runtime library, and it provides state capture and reconstruct functionalities. And these functions, calls to these functions are inserted by the AOT compiler. And the output of our compiler is a machine code binary, and that can be migrated across different ISAs. So in evaluation, our experiment addresses these 4 questions. First, how much runtime overhead does instrumentation add? Second, how much does it increase code size? Third, how fast are checkpoint and restoration? And fourth, how large are the snapshot? So first, runtime overhead. We compare Wanko with 2 AOT baselines, WebAssembly micro runtime AOT and WASM-H AOT. And you can see the black dotted line in this figure, and this represents the baseline of our compiler. And this compiler does not do any instrumentation. So the output of this compiler can't be migrated across different nodes. And without this machine code level instrumentation, Wanko performs similar to both of WebAssembly micro runtime, which is shown in orange, and WASM-H AOT, which is shown in red bars. And with instrumentation enabled, the average slowdown is 36%. This is shown in blue bars. And I think this overhead is acceptable given that we gain the ability to migrate across ISAs. Next, checkpoint and restoration times compared with CRU. CRU is a tool to migrate Linux process to another Linux. And it is limited to migrate the same. It is limited to migration between the same architecture. And across all benchmarks, Wanko achieves shorter checkpoint times than CRU. Restoration time varies more widely depending on program structure and heap layout, but still it remains competitive. Although our machine code level instrumentation enables fast migration operations. And next, snapshot size. Snapshot size is another advantage. We compare the snapshot size of Wanko with that of CRU. As I mentioned before, CRU is to migrate Linux process, and Wanko max 1 to 26 times smaller snapshot size than CRU. And the next step in the next evaluation, we measure the code size, and the instrumentation does increase code size. At the machine code level, it roughly doubles the binary size, about 2 to 2.5 times larger. For comparison, we also implemented WASM level instrumentation using AOT. AOT is one of the passes implemented in WASM optimizer, which transform WebAssembly bytecode, and output is also WebAssembly bytecode. And it turns out that this WASM level instrumentation produces more than 4 times increase. It's worse than machine code level instrumentation. So our approach achieves a good balance between functionality of live migration and compactness of code size. So in conclusion, we developed a WebAssembly compiler that supports live migration by instrumenting machine code. And our proposed method achieves both portability and good performance. And this imposes 36% of runtime overhead in average. And last, future work includes external state capturing, including file system and TCP and UDP socket, and further reduction of the runtime overhead. That's all. Thank you.
Thank you very much. Any question or comment?
So there is a fledgling standard for core dump formats across engines. It doesn't include, as far as I know, it doesn't include the local variables and state. I'm curious your thoughts about being portable across runtimes, so that you could have snapshots that are portable across runtimes.
Sorry, can you repeat the question again?
I'm curious your thoughts about portability of your snapshots across multiple different runtimes.
Mm-hmm. So the question is, if I understand correctly, the question is that the snapshot of our approach is portable across different WebAssembly runtime. So the answer is yes, and we designed a snapshot for this purpose. And basically, our snapshot contains WebAssembly call stack, and each call frame contains a program counter, and in the bottom, for the middle of call stack, it might be a return program counter, and the snapshot also contains global variables and linear memory, and it corresponds to a state of WebAssembly interpreter. So I think we can achieve also portability across different runtimes, but we need to implement state reconstruct and checkpoint mechanism for different runtimes.
Nice, thanks.
Thank you.
Okay, any other question, comment? Also, do you have any say idea for the reduction of runtime overhead?
Is a question.
Is it possible to reduce the frequency of the migration point to improve performance?
So I think to reduce migration point means program can't respond shortly after it catches migration request. So
I think there is a trade-off between the delay before the migration
yes,
and the overhead.
yes. So I think we can reduce significantly migration point, but we need to investigate this trade-off between this delay and performance. Thank you.
Thank you. Any other question?
to assume that your source and destination have the same set of capabilities.
So what do you mean by capability?
Where, like file system permissions and permissions for other operating system level interaction.
So what is your question?
Do you assume the same set of capabilities at the source and destination of
Mhm.
migration?
Oh, so in the current implementation, we only focus on core specification of WebAssembly, and it doesn't contain functionality such as calling to system calls and opening files and socket. So we only focus on migrating core WebAssembly state. So it only contains basic value stack in WebAssembly virtual machines. So yeah, so I think supporting file system and you mentioned as a capability. So it is one of the future works